This video is going to talk about how we actually show that a function is continuous at a point. Uh, and again, I'm going to save definition of continuity for later. This is just how we show it. And the way we do it is by eliminating the types of discontinuities. So a function f of x is continuous at some point that I'm going to call x equals a. Remember, IFF stands for if and only if. So it works both ways. So it's if a function is continuous at x equals a, these three things are going to be true. And if these three things are true, the function is continuous at x equals a. So the first thing we do is we want to see if the two-sided limit exists. And that's important. This is two-sided, which means the left-hand limit and the right-hand limit have to be the same. If they're the same and this limit exists, that eliminates whether it would be a jump, because if the left and right hand limits were different, we'd have a jump. Or if the left and right hand limits were going off to infinity or negative infinity, that would be a vertical asymptote. So if the limit as x approaches a from both sides exists, that eliminates vertical asymptotes and jumps. Well, next we want to see if the function exists at a. In other words, we want to know what is the value of f of a. If it has a value, then there's not a hole and there's not an oscillation. And then if the limit is equal to the function value, that checks to see was a point moved, the other removable discontinuity. And if all three of these are true, we have eliminated all of the different discontinuities, therefore the function would have to be continuous. So kind of an example here is just a random sketch of a graph. And we want to show, in other words, algebraically show that whether or not f is continuous here at 2. Now I know looking at the graph we can see, oh, there's a hole here. But that just is by looking at it. We need to actually show that's actually accurate. So the first thing is finding the two-sided limit. So that means I need to know what's the limit as x approaches 2 from the left of f, and what's the limit as x approaches 2 from the right for f. As I'm approaching 2 from the left, my f values are going down, 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 and approaching 0. As I'm approaching x equals 2 from the right, it's just horizontal here, and my y values are all 0. So from this, I can say that the limit as x approaches 2 from both sides of f is 0, so that does exist. And that makes sense because, remember, this is only eliminating whether we have a vertical asymptote or a jump. And we can see from the graph there's not a vertical asymptote and there's not a jump there. So the next thing we have to do is we need to actually know what is f of 2. Now in this case, we have a hole there, and looking, I don't see any point that's been moved. So f of 2 does not exist. In other words, remember, the whole point of this is to see, do we have a hole or an oscillation? And we can see from the graph we have a hole. So that means that, therefore, and the little triangle of dots means therefore, f of x is not continuous at x equals 2, since f of 2 does not exist. But then f of 2, here at 2, we do have a removable discontinuity. And remember, it's called removable because it means we can actually remove the discontinuity. We can make it continuous. So what could we do to make this continuous? It's actually really basic. All we have to do is fill in the hole. In other words, we define f of 2 to equal 0. And that would fill in the hole, and it would make our function continuous.